Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Akash Lal to you. Akash is a graduate student at the University of Wisconsin, and he's about to wrap up his dissertation on interprocedural analysis of concurrent programs. Very exciting stuff. He was advised by Professor Tom Reps over there, and he is going to join Microsoft Research India starting in the fall. And he's going to tell us about his dissertation work today.
Thank you for the introduction. Is microphone on? I think it is. All right, let's get started. So this is a modified version of my job talk. I got rid of most of the fluff, and I don't think I need to motivate the need for verification. I'm sure everyone here has had some disturbing experience with software failure. My recent experience was I was playing Diablo, which is a computer game, and I was about to kill the big boss when the program crashed. And that was pretty disturbing. I had to do it all the way, work up all the way again. So not only is software everywhere, software is also getting concurrent. Intel just released an 80-core chip for teraflop computations, and that might be coming to desktop soon. And as software gets more concurrent, the bugs are getting more complicated, and we need verification of concurrent programs. And as we all know, testing is not very effective when it comes to concurrent programs, because if you execute the same trace with one interleaving, the bug doesn't show up, but a different interleaving, the bug, there's a crash. So even when you fix the input to a concurrent program, there is still a lot of non-determinism, and you're not sure if you've tested the program enough that you've ruled out the bugs. So not only is testing hard, but reasoning about concurrent software is also hard. So this is, I'm going to tell you the Bluetooth driver story, which is catching up in the verification community. In 2004, Kadir and Wu, they did this tool called KISS, and they found a bug, an assertion violation in the version of the Bluetooth driver. And they released a fixed version for it. In 2006, the same assertion violation was found in the fixed version. In 2008, the same assertion violation was found in the fixed version. Now, this story has to be taken with a grain of salt, because every time a new fixed version was proposed, some part of the story was lost. And well, so this bug was essentially violated an OS invariant, which they were not aware of, and which was implicit in the previous work. But in any case, we know reasoning about concurrent programs is hard. So what I'm going to be talking about is my thesis work on verification of concurrent programs and my contributions to it. I know that in the abstract I promised the verification of machine code as well, but I left that out just to spend more time here, and I can talk about my verification of machine code offline. All right, so let's look at the problem of concurrency a little harder, a little more closely. So in terms of testing, we can say concurrency is hard, because even with a fixed input, there can be an exponential number of behaviors in the program. That's why testing is hard. You need to run the program so many number of times. But in verification, we're anyway, whether you're doing verification of sequential programs or concurrent programs, we anyway have to reason about an unbounded number of behaviors. So what's an exponential factor of an unbounded number? So the way to answer that question is let's look at how we actually verify programs. We typically use some sort of abstraction, which is that you consider an over-approximation of the actual program, and you try to verify that over-approximated model. And what happens is, even with the common abstractions that we have used for sequential programs, the presence of concurrency makes the analysis harder, even for those abstractions. So if you take this sort of the simplest kind of abstractions, which is finite abstractions, in the sequential case, it's all polynomial time, but in the concurrent case, it becomes either p-space complete or undecidable. And what that means is, even with the abstractions we have been using, the ones we are familiar with, we can't use them when it comes to concurrent programs. So the solution we choose is that we're not going to do full verification of concurrent programs, but we're going to be somewhere in between being sequential and concurrent, which is what we call context-bounded concurrency. So context-bounded analysis is the analysis of concurrent programs when you fix a bound on the number of context switches that can happen between different threads. So what Shaz had proposed in his previous work was to bound the number of context switches, but we have a slightly different notion, which is bounding the number of execution contexts. These two notions coincide for the case of two threads, and I'll start distinguishing them when I talk about multiple threads. So there is a history to context-bounded analysis. I think Shaz started it with this tool Chess that did verification of concurrent programs with two context switches, and they found a lot of bugs in drivers. And they had a result which said that for finite data abstractions, the problem of context-bounded analysis is decidable. And subsequently, they have this wonderful tool Chess that does systematic enumeration of all interleavings given a test harness, and they found many bugs in a few context switches. So this leads to the question, what can we do if we don't fix a test harness? If you don't fix a test input, can we still do verification under a context bound? So my work starts here. First thing we showed was that this bubble is not just decidable, it's NP complete. Then we gave decidability under more complicated abstractions, including infinite state ones. But except for KISS, all this work was still theoretical. And we subsequently extended it to do practical verification of concurrent programs. And these two works, so I'm not going to be talking about the first one, which involved an interesting mix of automata and matrices. But what that showed is, this decidability result, what that showed is that the world of context-bounded analysis is not that much different from sequential analysis. And subsequently, we showed that we can, in fact, do context-bounded analysis using sequential analysis. And this is what I'll be talking about. So just to summarize, what context-bounded analysis has done for us is that it's added a third column to our table, saying that, well, maybe full concurrency was too hard, but context-bounded analysis has a better hope of scaling. All right, so let's just get down to what we could do with context-bounded analysis. So we try to test two hypotheses. First, that we wanted to show that most bugs can be found in few context switches, because only then would context-bounded analysis would really be useful. And also in terms of performance, that context-bounded analysis can compete well with full verification techniques. So we did our study in this tool called DD-Verify, which is like SLAM, except that it works on concurrent programs. So it has a predicate abstraction front end that produces a concurrent Boolean model. So every thread in the program is abstracted to a Boolean program. And then the way they've structured it right now is that this Boolean model is fed to their model checker SMV, and that either says that the program is correct, or it returns a counterexample, and there's a refinement loop there. And what we did was we took out their model checker SMV and we put our own model checker that does context-bounded analysis, and we fed it some context-bound K. And we compared what SMV could achieve versus what we could achieve. And this is what we found. So every dot here is a different test example. This is the time that our tool took, and this is the time that SMV took. So it's a log-log plot. And every dot is classified into two categories. Either that SMV said that the program was correct, meaning that there were no bugs in that program, or SMV said that the program is buggy. So the ground truth of whether the program is correct or buggy was as SMV said. And what we find is, first of all, the median speed up was about 30 times. So for all the dots that are buggy, all the cases that are buggy, this number says the number of context switches before we found the very same bug. And what this shows is that our tool, with a bound of k equals 7, was able to find all the bugs that SMV could find. So what that means is in this case, all bugs occurred in 6 context switches or fewer. We were able to find it. And with a bound of k equals 7, we were 30 times faster than SMV.
So one question, for the correct ones, what was the k you fed to your tool?
K equals 7.
7 for all of them. Okay.
But SMB didn't have a K, right?
No, SMB is full verification. Okay, so that's what we could do. Now let's get down to how we build our tool that does context-bound analysis. And the way this is structured is that we take a context-bound K, we take in the concurrent program, and we do a reduction into a sequential program such that checking properties of this sequential program is sufficient to conclude properties of this concurrent program under that context bound.
Sorry, one question.
Yes.
Can you go back?
To this?
Yeah. And these samples that you have, how many threads that they have?
Most of them will have 2 threads, but they can have more.
And you expect this, so you 30 times speed up.
Mm-hmm.
You expect that number to increase, your speed up to increase as you increase the number of threads, or decrease?
Well, that's a good question. It would really depend on the program, but more threads I would expect our speed up to increase. I will give you some evidence later. Yes?
And I was curious also about this data. K equals 7, why 7? Did you try 6 and then there are lots of things that didn't,
Yes.
right?
Yes.
Okay. So
Yes. That's why K equals 7, because I knew I could find all bugs, and I had to give an odd number. So, yeah, that's why. So,
Yeah, so this is not interprocedural.
so the programs that DD Verify produces, the Boolean programs, they have all procedures inlined. So all the Boolean models are single procedure. And they had to do this because SMV could not handle procedures. But our tool actually can handle procedures. So there's hope of extending DD Verify so that it produces more complicated models.
So, but for example, what you did was you took the single procedure thing and then did context-bounded analysis on it.
Yes.
You did not change their translation so that they emitted.
No.
Okay.
I mean, this is not open source, so I could not do that.
And did you do any comparison with tools like Spin?
I have. I will show them later on. Anything else? So I'll have some more results later on. All right, so we do this reduction to sequential programs, and what that means is that we can now borrow over all the cool stuff that we did in the sequential world and directly apply it to the concurrent world. And in whatever I describe next, we only focus on safety properties, and that too only assertion checking. And if we have other sorts of properties, like for example, the array should never be cleared between an insert and an increment to the length, then we instrument the program so that what we verify are just assertions. So this is just to say that we're only going to worry about assertion checking, and other properties can be reduced to it. Okay, so start off by considering just the case of 2 threads. So our model of a program is that these 2 threads have their own local memory, and they communicate through shared memory. And in whatever I describe next, it would be useful to think of a thread as just describing a transition system. So it takes in a shared state S1, its own local state L1, runs for a while and produces this and changes the shared state to S2 and changes the local state to L2. So every thread is just describing a transition system. Now in the case of 2 threads, the execution will proceed with the control alternating between the 2 threads. So first T1 goes, then T2, then T1, then T2, then T1, and so on. And the problem with the analysis of concurrent programs is when you do execute one thread, so T1 executes, it changes S1, L1 to S2, L2. Now the shared state has to go here to T2. It needs to know where it has to start from, but the local state has to be saved and then restored when T1 gets execution back again. And whenever there's a split in the way the data is flowing, you risk losing correlation between the two. And that happens because what we're doing is that we're not propagating a single state, but what we're propagating are sets of states, set of all reachable states. So when we feed in S1, L1 to T1, it can reach this huge number of states, Si, Li. And the set Si has to be passed to T2, but the set Li has to be saved and then restored. But what happens here is that you list the correlation between which Si or which Sj prime is related to which Li. And the way that's typically solved is that you start pairing local states. So you put in the local state of T2 in your state tuple. So you say it's going to be S1, L1, N1, and now you don't have any forks. But what happens is now you started pairing local states, and that gives you a state space explosion. So you have an exponential growth with the number of threads. And that's what makes concurrent analysis hard, because you have to consider the local states of all of the threads. So the way we're going to solve our problem is slightly different. What we say is that, so this fork is bad. So we're not going to do a fork. And instead what we're going to analyze is that we're going to analyze T1 first, be done with it, and then we'll start analyzing T2. And the way we're going to simulate context switches in the execution of T1 is that we're just going to guess what T2 did. So during the execution of T1, if you want to do a context switch, we just guessed a new shared state S3. So we just guessed that the execution of T2 is going to change the shared state from S2 to S3. And when we finally get to T2, we're going to verify whether our guess was correct or not. So more formally, what we're going to do is we're going to guess k minus 1 global states, where k is the number of context switches. So we say S1 is the initial state of the shared memory where the program is supposed to start execution. And S2 to Sk are guesses. So basically, they're just arbitrary shared states. Sorry, k is not the number of context switches. K is the number of chances that each thread gets to run. So the number of context switches is 2k minus 1. All right. So the execution of T1 will look as follows. We start execution of T1 with S1 L1. So we use the first state S1. We start it off. We let it run for a while, and at some non-deterministically chosen point in time, we just use our next guess S2. So we change the shared state from S1 prime to S2, and we let it run again. Then we use our next guess S3, and so on till we exhaust all our guesses. And then we pass control to T2. And now for T2, these S1 primes, these prime states are going to act as the guesses. So you start with S1 prime, let it run for a while, and then change it to S2 prime, let it run for a while, and so on. And what this means is that right here we've guessed that the first time that T2 gets a chance to run, it has to change the shared state from S1 prime to S2. But it actually changes it from S1 prime to S1 double prime. So we have a check in the end that says S1 double prime should be equal to S2, meaning all the guesses that T1 made, T2 actually satisfied those guesses. And if we pass all these checks, then we have these arrows equating these states. And if you get rid of redundant arrows, what we have is a valid interleaved execution of the concurrent program. And the good thing here is that the local states are short-circuited. They did not have to be saved and restored. They were just reused during an execution. So one thing that this is a strategy that we're going to use, guess and a check strategy. But in the next insight we use is that this guess and check is not something that's new to verification of programs. In fact, it's done all the time for the verification of sequential programs. So the problem for verification of sequential programs is that you need to guess an input for which the sequential program reaches a bad state. So you have to guess an input and check if a bad state was reachable. But in fact, the tools that do analysis of sequential programs don't do a guess and a check. They actually find the input for which a bad state is reachable. So we're going to use this intuition to do our guess and check strategy. And we do that by pushing all the guesses into the input state, and then we're going to ask a sequential analysis tool to find the input for which a bad state is reachable instead of just guessing it. So what this means is that the final sequential program that we produce is going to have k copies of the shared memory as input. Oh, something missing. So if the original concurrent program had 4 variables, w, x, y, z, and let's say k equals 3, then the input to the sequential program is going to be 3 copies of the shared memory and an extra counter I that's going to count from 1 to 3. And the way we change the data, we change the code is as follows. So let's say st is a program statement. Then tau of st comma I is a syntactic renaming of that statement where every global variable g is changed into its ith copy, and the local variables remain unchanged. And the way we transform each statement is, given a statement st, we produce this block of code in the sequential program. And what that does is it says if the value of I is 1, then operate on the first copy of the shared memory. If the value of I is 2, then operate on the second copy of the shared memory, and so on till I equals k. And if this is the code that simulates a context switch. So at a non-deterministic point in time, just increment the value of I and start using the next copy of the shared memory. And if I reaches the bound, then you reset it to 1 and you jump to the next thread. The way the assertions are transformed is that we add a new Boolean variable, no error, and that basically just records the value of that assertion in the current value of I. So what we do is we take the two threads, produce the sequential versions using the transformation I described on the previous slide, and then the concurrent program in which T1 and T2 are executing in parallel is going to be this sequential program, in which you execute T1s, then you execute T2s, then you have a checker, and then you assert that there was no error in the execution. So the way this sequential program executes is as follows. So the value of I starts with 1. In that case, T1s is going to do exactly what T1 did, but on the first copy of the shared memory. Then it reaches some point at which it increments the value of I. So I becomes 2, then it's just going to start operating on the second copy of the shared memory. And then I becomes 3, it operates on the third copy. Then you pass control to T2, reset the value of I to 1. T2s operates on the first copy of the shared memory, then it operates on the second copy, then it operates on the third copy. And then we pass control to a checker that's going to check that this state was equal to that state. So in this case, T1 assumed that the T2 is going to change the shared state from this guy to that guy, but it actually changed it from this to this, so you check whether these two are the same or not. So this checker just checks this equals that, and this equals that. And if the checker passes, then this is a reachable state of the concurrent program, and we can do our assertion checking, assertion checking on this reachable state. So the good things about this reduction is that the local state of the program does not increase. So the local state of this sequential program is only the sum of the sizes of the local states of the original threads. A naive reduction would have a product here. So we got a product down to a sum. In terms of static analysis, the global state of our sequential program has k times the number of variables because we had to introduce k copies of the shared memory. In terms of model checking, the shared space grows exponentially with k because k times the number of variables means that your state space increases by a factor of k. So this sort of means that there is no free lunch. The problem is NP complete in k, and we're sort of bound to have an algorithm that's going to be exponential in k. And the main idea that we've used here is that we've reduced the control non-determinism that comes from concurrency into data non-determinism, and data non-determinism is something that's already handled in the sequential world. All right, so the situation changes slightly when we have multiple threads. So let's consider the case when we have n threads and k context switches. So the problem in that case is that there are too many thread schedulings that can happen in such a program. So you can have either T1 going first, then T5, then T2, then T4, or you can have T1, T3, T4, T2, and so on. You can have n minus 1 to the k a number of thread schedulings. And just enumerating each of them is going to make even the best case complexity exponential in k. And that's something that we want to avoid. So our solution is that we're going to consider only one thread schedule, and that's going to be a round robin thread schedule of length n times k. So in this round robin schedule, every thread gets k chances to run. So it's k execution context per thread. And the properties of exploring just this one round robin schedule is that it considers strictly more behaviors than all thread schedules with k context switches or fewer. And the reason for this is as follows. So supposing we have this thread schedule which is not round robin and has 2 context switches. This thread schedule is simulated by a round robin schedule of length 2 times 3, which is this one. But in this round robin schedule, what happens is T2 decides to do nothing when it gets a chance to execute, then T1 here decides to do nothing, and T3 here decides to do nothing. So this way, round robin schedules can simulate other schedules which are not round robin. So what we have is, if we consider one round robin thread schedule of length n times k, then we consider all behaviors with k context switches or fewer. But we can get also other behaviors that have more than k context switches, because this schedule has nk minus 1 number of context switches. And the other good thing about using this round robin thread schedule is the sequential program is producing the sequential program that simulates this round robin thread schedule is easy, and that just looks like that. So you just run T1 first, then T2, then T3, and so on. And the reason why this works is as follows. When T1s runs, it operates on its k copies of the shared memory, and because in the round robin schedule T1 always passes on the state to T2, we just have to run T2 next. So when we run T2 next, it just picks up what T1 left it at. So in terms of this timeline, what we had to do here was we sort of did the execution of T1 for its 3 execution contexts, the 3 chances that it got to run, and T2 we know has to start off from where T1 left off. So T2 has to go next, and similarly T3 has to go next, and T3 always picks up the state from T2. So the advantage here was we only had to make the number of guesses we had to make was not proportional to the number of context switches. We only had to guess here where T1 started off its next execution context. So the guesses are only going to be this state and that state, because we know where T2 is going to start off, and we know where T3 is going to start off. So even though we consider a round robin thread schedule of length n times k, the sequential program has only k times more variables. It only needs k more copies.
This is a little confusing. In your second bullet, you go from T1 to Tn, but then you have to again execute T1, right?
Here?
Yeah.
Yeah. So in the concurrent program, yes. In the concurrent program, yes, but not in this sequential program. The reason is, when we run T1, we're going to run all its execution contexts at that time. So in this picture, let's say the value of k is 3.
Yes.
So T1 gets 3 chances to run. So T1s operates on 3 copies of the shared memory.
Yes. Okay.
So it already does all its execution context when it gets to run. Right. And when it's done, then T2 does all its execution contexts, and then T3 does all its execution contexts. So what we have is a round robin. We simulated a round robin schedule in which every thread got 3 chances to run for 3 threads.
So, but to simulate k, all executions of k context switches, you have to give each thread n times k chances to run, right?
Just k chances to run, not n times k.
Just k chances to run.
Right, because if you have k context switches, a thread can at most get k chances to run.
Sure, okay, that's right.
So we're giving every thread k chances to run, and we're considering a round robin schedule in which all of them get k chances. Yes?
So every time you get a chance to run, you could be starting anywhere and ending anywhere. So
right.
I don't see any. I don't see why you have to run them in k times. Because you stop non-deterministically at any point in time, and then so it's.
So I guess one thing is, each of these threads know where they're going to start. So like for example, T2 knows that it has to start from a state that T1 left you at. So T2 is picking up everything that T1 did automatically, right? So
no, I'm just, let's look at the second and third execution of T1.
mm-hmm.
Is there any behavior that could appear in the second part but which could not appear in the third part? Or vice versa? I think that it's a mark.
Well, I mean, it could do more here, right? So okay, so this is in terms of the global state, but what is kept is the local state. So when we switch to use the next copy of the shared memory, we're reusing the local state that it left off at. So the local state is constraining how T1 is going forward. Right? Even though the global state is sort of reset here when you start using the next guess, the local state is saved. The same, you have to reuse the same local state. Right? So if there were no local state, what you're saying is correct, that all these three would be isomorphic to each other. We're just repeating the same thing thrice. But it's the local state that sort of ties them together, constrains them to one particular behavior.
But every possible initial local state for the third iteration could have been a possible initial state for the second iteration.
I think that he's not doing that for the local states. What you're saying is true only for global states. He starts from an arbitrary global state but preserves the local state.
I know, but in the, let's say you started from statement 1 and executed till 5, and then in the second iteration you executed from 5 to 8. In the very first shot, you could have gone from 1 to 8.
Right, but the difference is that there was state reset, a new global state at statement 5.
Yes.
So in some
5 to 8 in one execution would be executed from a different state. In the other case, 1 to 8 is executed without any interruption. Right? That's the difference.
maybe.
Okay, yeah. I guess, but there could be, I mean, if you were to compute summaries, you could do something better. There is some redundancy going on there.
We are going to compute summaries. I will come to that. In some sense, what's happening here is that when we're running T1, we're considering a vector of global states. So when we give it 3 chances to run, we're asking it to tell us what's the 3 sequences of global state changes that it can make. So when we're going to summarize the behavior of T1s, we're going to summarize it as a string of length 6, which says that there is an execution of T1 that goes from state this to state that, and if there's a context switch that leaves it at this state, then it changes the state to that one, and if there's a context switch that changes the state here, then it can leave it at that one. So I will come to that a bit later. All right, just to summarize what we did for multiple threads. So we compare 2 things, either considering k context switches and all thread schedules with k context switches, versus what we said, which is k execution contexts per thread and round-robin thread scheduling. Then we get strictly more behaviors. We only consider 1 thread schedule, so we avoid this exponential factor. And the complexity remains the same because in either case we had to make k guesses and not more. So it's win-win and draw. All right, some more results. So another property of the reduction with multiple threads is that because the number of guesses are only dependent on k and not on n, the size of this sequential program is only linearly grows with the number of threads. So you sort of expect that if you have more threads, your analysis should only grow linearly. The analysis time should only grow linearly. And that sort of, there is some evidence here. So in this graph, we took a Bluetooth driver. I think it's a fixed version of the Bluetooth driver. these are the number of threads. We vary the number of threads, and we give each thread 4 chances to run. So we're systematically adding more and more threads, and the time grows linearly, at least for a little bit. After a while, it jumps up. We don't know why it jumps up, but at least it was linear for some time. This sort of says there is no free lunch. In this case, we fix the number of threads to be 3, and we vary the number of execution contexts per thread. And the time grows exponentially with the number of execution contexts per thread. So this is a comparison with spin. So there is a benchmark suite called BEAM, B-E-E-M, that has a whole bunch of examples meant for explicit state model checkers like spin. So we took some common mutual exclusion algorithms, and this is, I think, a network protocol. And the benchmark suite in each case has a correct and a buggy instance. And what we found is that in the buggy version, we always were able to find the bug with a small number of execution contexts per thread, either 2 or 3. Excuse me. And we compared fairly well with spin.
So this number of shared is the number of Boolean shared variables?
Boolean shared variables.
So there's the MSMIE has 23 Boolean shared variables and 20 threads. And spin finishes in 31 seconds.
There's a lot of redundancy here. So one other.
Is spin running with partial order reduction on?
I think so.
Okay.
I think so. I mean, one thing to take out here is another thing to take out is so spin, because it's explicit state, it has a termination. If the set of states is finite, then it's going to terminate. But we sort of don't have any such guarantee when we do context-bounded analysis. We sort of don't check if we already visited a state before. So I mean, if we keep increasing the bound, our time is going to keep growing, even though it's exploring the same states again and again. So that's something we need to put in the future.
So I missed one thing. So how do you actually do the analysis on the sequential program that you got?
Right. Okay. So that's a good point. We do symbolic model checking. So we used a tool like Moped that uses BDDs to construct function summaries and use PDS-based analysis.
But actually, that's not really any of these your experiments. I mean, you could have used SME.
We could have used SME, right? So but yeah, we just supported one thing. Yeah, so sort of this comparison isn't fair because we're doing symbolic model checking here, whereas spin is explicit state. So, okay. So one of the downsides of this reduction is that is all these guesses that we make, and these guesses lead us to, most of the times will lead us to behaviors that are actually not possible in the concurrent state. So we're going to explore a lot of redundant behaviors when we explore T1s and T2s, but the checker is going to rule out most of them, and only a few will be valid concurrent behaviors. So what we're going to do is we're going to say that, okay, the way we're going to solve this is we're not going to analyze them in this order, but we're going to analyze them side by side. And the way we do this is by constructing thread summaries. For every thread, we're going to construct thread summaries, and we're going to build them for T1s and T2s at the same time. So a summary is going to look as follows. So a summary of T1 will have a value of k, which is the number of execution contexts we've considered so far. G1 and G2 are vectors of global states, shared states, and the length of those vectors is equal to k. So if the value of k is 3, then the summary is going to look as follows. You're going to start from, the summary says that T1s, when started in this state, can leave us in this state. So the local state is not copied, so we have just one local state, but there are k copies of the global state. So this is a summary, what the summary means. And the way these summaries are processed are either they are processed in an intra-thread fashion. So if there is a statement st in T1s, so we know every statement operates on the last copy of the shared memory. So if st is something that can take GL2 to G prime L3, meaning that it can take this state, modify it to that state, then this is how a summary is updated. Then the summary can go from G1 L1 to G2 G prime L3. So G1 L1, G2 prime, G prime, G2 G prime L3.
So you have G2 is a vector, but G is just a single guy.
So G2 is a vector of 2 in this case. So this bracket thing is a tupling operator.
Oh, okay. I see, yeah.
So we say that if G is the last component in this vector, so if G is this thing, and the statement ST changes G to G prime.
Let me ask my question again.
Yeah.
Is the size of G1 1 greater than the size of G2 vector?
Yes.
I see.
So pictorially, this is just this is all that you need to know. It's just an intra-thread update of the summary. Okay, and the way the eager analysis work is that it updates a summary as follows. It says that if we have, for a value of k, the summary says we can go from G1 L1 to G2 L2. Then we increment the value of k, meaning that we're going to consider the next execution context, and we're going to extend our vector of global state by any state G here. So this rule applies for all G. So this is like making a guess for the next execution context. We make all possible guesses. So in this case, this is what the eager analysis will look like. But what we're going to do in our lazy analysis is that we're not going to update this E1 for all G, but we're only going to update it for those G that actually occur on a valid concurrent behavior. And the way we do it is as follows. So the rule is going to look the same as before, as for a eager analysis. So all I've done here is that I've expanded the vector to be where the first component is init, which is the initial state of the shared memory. And we're going to update this component. I should use the pointer. We're going to update the first component with a G, and we're going to update the second vector with also the same G. But the way we pick this G is going to be different now. So this E1 says that T1 can go from init D L1 to G2 L2. Init D L1 to G2 L2. And now we're going to look at the summary of T2, what T2 can do. So in this case, the summary says that it can go from G2 L3 to DG L4. And what we've done is we have an implicit checking step here. We've said that this G2 equals that G2. So G2 used here has to be the same as the G2 used there, which is one of the steps that the checker needs to do. The other thing is that this D equals this D, because what that means is that there is a valid concurrent behavior here that goes from init to the first component here, which is the same as the first component there, which goes there, which is the same as this one, which goes there, that, and so on. So this condition enforces that we're going to pass the checker, and which means that we have a valid concurrent behavior, and in which case this G is going to be that G. So we extend our summary using just that G. So it's similar. So this is the only rule that changes when we go from an eager analysis to a lazy analysis, and this enforces that all the guesses we make are actually valid guesses. So we don't need a checker in the end.
It can be parallelized also, right? You can, for example, run the summary computation for the different threads.
Yes.
In separate threads almost.
Yes.
The second use of the word threads is in real
computation thread. Right. Yeah. So that holds more true for the eager analysis, because there is absolutely no communication between the summaries of the different threads till you get to the checker phase. So you can construct the summaries of each of the threads independently.
I see.
Whereas in the lazy analysis, you sort of have to communicate every time you increment the value of k.
You wouldn't get that if you were using a sequential, a tool for analyzing sequential program that would be compositional. Not quite, because it's case sensitive here. Right?
Yes, yeah.
So you could encode it in such a, I don't know.
Yeah,
How
so
does that compare?
right. So we couldn't figure out a way of doing this using a reduction to a sequential program, because we were sort of, once we produce a sequential program, we're sort of restricted to analyze the program in program order in some sense. But there has been subsequent work. There's going to be a paper at CAV that gives a lazy reduction. So analysis of the sequential program that they produce is actually corresponds to our lazy analysis. But there's a slightly different reduction. Yes?
So how is this different from iteratively increasing the context bound?
This is iteratively increasing the context bound. Yeah, but you sort of do it in lockstep in that you know that these two summaries are being computed side by side. When you want to increment the value of k, you increment each of them and then you go forward.
I mean, another nice thing about this is that it is like what Sumit is saying, completely iterative. You can just keep chugging along.
Right.
And you get to reuse whatever happened in previous context. And the other thing, if you just construct a sequential program, you run it for k. Then if you didn't find a bug and you want to run it for k+1, now you have lost all that work. You have to transform the program again and run it.
Right. That's true.
Unless you memorize your summaries for k-1. That's not correct. That's not straightforward, right?
Well,
Yeah, you can do that, but the way this, if you're producing a new sequential program, then sort of you're rerunning the sequential analysis again. If you have a smart sequential analysis that knows how the program changed, then it's okay.
Because you're sort of running it again, right? I mean, maybe it's an engineering issue, but it's...
But the behavior that the behavior that you observe with k+1 are going to be a superset of what you explore that you observe for k.
Yes.
And so in that sense, it's monotonic, and so
Yes.
it could be engineered.
Yes, it could be, definitely.
It's not like k+1 is a completely different program than
right.
k, and then you could not reuse basically.
Right.
Sorry.
All right, let me get a little bit into future work. Some of the things I would like to be working on at Bangalore. So I told you the Bluetooth driver story, but what I didn't tell you is why those bugs were missed. So this was case, so it did analysis for 2 context switches. This was a tool that can go up to more context switches, so they considered 4 and found a new bug. This considered 2 stopper processes, whereas both of these previous work considered just 1 stopper process, and they were able to find another bug. And so what this is one limitation that context bounded analysis is always going to have, in that you're always going to miss bugs. There's always potential of missing bugs. And what I would like to do is even for my hypothesis is that even for doing full verification, context bounded analysis is a good approach in getting there. So there are a few observations that sort of lead me to believe this. The first is a study that Shaz did in PLDI 07, which was to say that doing context bounded analysis, you cover a large portion of the interesting behavior in a few context switches. So if you have a handle on most of the behaviors, can you make a guess on the set of all behaviors? And the second observation that we made is that mutual exclusion invariants can often be found just by looking at behaviors with 2 context switches. And I'll give you an example in the next slide. But the hypothesis here is that you're going to do context bounded analysis, get to know something about how the program is behaving, then generalize from that and get an abstraction for doing full verification of the concurrent program. So let's look at how CBA can help in mutual exclusion. So this is a program in which the access to X is always protected by lock LCK. And if you look at this, the sort of invariants we want to prove is, or the negation of the invariant is that a data trace can occur whenever a different thread, when it started with the lock acquired, then it can eventually access X. So if you start a different thread with the lock acquired and it accesses X, that means there can be a data trace in this program. Or you start the thread with lock equals 0, then it's able to access X and keep lock to be 0. So this is sort of the negation of the invariant that says you can only access lock when you can only access X when lock is acquired.
I don't understand what you're saying here.
is that data race? First of all, there's only one thread here.
There's only one thread here. So we know what this thread looks like, and we want to know when can there still be data races on this thread, not knowing what the other threads are. So this is the obligations on the other threads.
Okay.
So there will be a data race if the other thread, when it started with the value lock equals 1, then it's able to access X.
Why would there be a data race on that thread?
Because the execution of T1, you can get to this point. So lock is acquired, then you switch to the next thread, and it, because it satisfies this, is going to access X, and then you access X here, and then you have a data race.
Okay.
And similarly, the other thing here is that you context switch here, so the value of lock is 0. Then the second thread accesses X, but keeps the value of lock equals 0. Then you can come here, and then you can access X. So these are the things that you would want to find out looking at this program. And context-bounded analysis allows you to find this, and that is as follows. So we consider T1s. So we know the source code of T1, so we consider T1s with k equals 2. We're giving it T1s, T1 2 chances to run. And we're going to consider the set of its behaviors from the start of its execution till a point when it accesses X. And because k equals 2, T1s operates on 2 copies of the shared memory. So in this case, the only shared thing is lock. So we have 2 copies of the variable lock. And so initially, the value of lock is 0. And then we want to fill in these question marks. So basically, we're constructing the summary from start to access of X. And we're going to look at what the summary looks like. So if we run the analysis, we're going to find 2 things in the summary. One is this, which says the value of lock is 0. It remains 0. There's a context switch, lock is 0, and then lock is 1, which is actually this invariant. Because it's saying that, so this thread can get to an access of X when there was a context switch that didn't change the value of lock. So there will be a data race when the other thread can access X, starting in lock equals 0, it remains lock equals 1. So this basically is putting an assumption on the next thread. If the next thread can do this, then there will be a data race. And the other thing we find in the summary is this, that if the execution of T1s goes from 0 to 1, then there is a context switch in some state, and that is supposed to be this. So basically means that if we start the other thread with lock equals 1, no matter how it changes the value of lock, if it's still able to access X, then there's going to be a data race. So the thing to take out here is by looking at T1s, you know the obligations on what the other threads can do to reach error. So you get an over approximation of what things can force you to error. And once you have these invariants, then the idea is to construct a sort of a predicate abstraction based proof where we just abstract the other threads using just these invariants. So it's sufficient to check these invariants on the other threads, and then we know that there are no data races.
So, but what I don't understand is that you are trying to find some assumption on the environment that is going to help you prove the property locally.
Yes.
What prevents you from coming up with the assumption that the environment doesn't do anything?
I don't know the answer to that. So the summary we construct here is a set of all behaviors of T1, right? So we're considering all behaviors of T1. And the things we find from here, these 2 things, they are sufficient to rule out all bugs for 2 context switches.
So in terms of what you're saying is that maybe you are trying to find out the most relaxed assumption about the environment, because what you're doing is you're completely havocing the state,
right?
And then you're saying, okay, what is the minimal constraint, like the weakest constraint on it somehow?
Right.
Okay, I see.
So the thing to take here is when you do find this weak invariant, it sort of can give you the right thing. But the only thing that it ensures is that if you do enforce this on the other threads, then you're ruling out bugs with 2 context switches. But the hope is that they're still general enough that they're going to still allow you to verify for any number of context switches. So it's basically you find the assumptions using an under approximation, and those assumptions just happen to be right for any number of context switches.
You'll have to somehow write that assumption, rewrite that assumption, pretending that there are lots of context switches. I mean, when you come up with it, right, you will have like x0, x1, x2, something like that, some finite number of variables, but you'll have to somehow write it more
right.
as in a parameterized
Right.
way.
So like in this example, there's sort of just one context switch here because you're considering just one run. But you sort of look at what's important here, log equals 1, log equals 0. And then you use those predicates to abstract the program. And hopefully that should work. Maybe. And so this was a simple example in which we had a simple variable lock. But the same thing applies in a more complicated setting where in this case there are two variables, old and state, and they together enforce mutual exclusion on the axis of variable x. So this is Decker's mutual exclusion, and it's basically there's a sort of an implicit lock, and the lock is acquired when the value of old is 0 and the value of state is 1. So the same reasoning also applies in more complicated settings when you're not really sure what the locking invariant is. All right, so something else I wanted to do, which Shaz has already done partially, is to apply the context-bounded analysis on low-level code. And one thing that's missing in the reduction that does not allow us to do this is that you still need to know what is shared and what is local. Because if you assume that everything is shared, then you're not really going to have an analysis that's going to scale. So you need to have knowledge about as much state that is local. And for programs like binaries, it's not really clear what's shared and what's local. So, well, okay, I have time. So one of the other things that bugs me a lot is writing stubs for the operating system. All static tools will have some stubs for modeling the operating system, modeling the environment, or some such thing. And they are never published. You never know which ones are the right ones, but they are extremely relevant for the performance of a tool. So what I'd like to do is to automate stub generation in some sense, so that everyone sort of have a benchmark of which stubs are relevant for which kind of properties, so that everyone can use the same stubs. And the way the challenges here is as follows. So, like for example, let's suppose this is the code for writing to a file. This is the actual operating system code that writes to a file. And supposing we're only interested in the property of knowing the size of that file. So from this code and knowing the property, we would like to produce this code that only just increments the value of the length of the file. If we're only interested in whether a program produces a Unix or a DOS file, then we're just interested in whether the input buffer contains a return, and in that case it's a Unix file or a DOS file, whichever is the case. So the challenges here is this is sort of like doing partial evaluation with respect to a property, and also instrumentation. So in this case, this was a new flag that was added, saying whether a file was Unix or a Unix file or not. So you want to do instrumentation of the property, and you want to do partial evaluation, and the goal is to produce a program that's sort of as deterministic as possible. So it's not just abstraction, but you want to have some certain more properties so that the stubs are actually useful when you use them. So the big thing I think is to know what we want to do after we do verification. So there has been a lot of work in ranking bug reports that verification tool produces. We know that a user can't go through all bug reports, so there are heuristics that sort the bug report according to relevance, and then you only look at the top few. So there's been a lot of work in that area, but there has not been enough work to say what happens when a verification tool comes back and says that yes, your property does hold. In that case, what happens is the user just says, well, I already knew that the property held, and moves on. So there is nothing much gained in that setting. And what we would like to do is have a way of making the information persist through different verification runs. Even when you have proved a program to be correct, you want that thing to persist in the program, either in the form of some language that humans can understand, or in the form of a language that machines can understand. So then the next time you do verification of the same program, you know something about what was there in the original program. And this has interesting things like, do we actually know how to write proofs for concurrent programs? Is there a good way of writing them? Most of the tools right now just do an exploration of all reachable states. And even though that can prove properties, it's not really a proof of the program. It's not something that you can write down. So there has to be some work on minimizing proofs, finding something that corresponds to a loop invariant for concurrent programs, and so on. And in certain settings, when you know that all a proof is doing is that it's proving mutual exclusion, then it's just easier to write it as saying that, look, these things are, there's a mutual exclusion there. And what I believe is that this, if you know how to write concurrent programs, then this can also influence future development work for writing concurrent programs, and also for designing languages that allow you to write better concurrent programs. And that's it. Thank you.
Questions? More questions?
Yes.
Note that the agenda on your last slide, not this one, the previous one, goes against all your talk here, where you were reducing concurrent analysis to sequential programs. So what's wrong with that for being with these approaches?
Well, the thing is still, we're not able to produce a proof of the concurrent program. So again, what we're doing is, the analysis is only just exploring all the set of reachable states. And there is no way of having that persist. No way of communicating that to a user. Even when I'm debugging the tool, that proof is completely useless to me. I have no idea whether the set is actually correct or incorrect. And if there's a way of, once you do prove that a program is correct, if you can just tinker around the proof and find out some nice properties of what it's actually trying to establish, then there might be a better hope of.
So I think there's a larger problem, which is I think an economic problem. I think that to some extent in the program analysis community, we have managed to put economic value on bug reports. And therefore there's this whole, like research and industry that has evolved around it. Mm-hmm. But to my knowledge, I don't know if anybody has managed to put economic value on proofs.
Right.
Or, I think that there's a lot of people who sort of believe that, but I don't think that in the widespread, software engineering community, anybody believes that there's any value in proofs.
Would you say the same thing holds for sequential program as well?
This is a broader issue, nothing to do with concurrency.
Okay.
Because, the attitude is exactly this. Your tool comes up and says, verified. Okay, what now? The programmer already believed that his program was correct.
Right.
What extra information you get giving the programmer?
It's because the tools are not sound, nor complete, etc. So whatever. So in that case, you have no feedback. You see, the tool was enabled. You cannot distinguish what's sound.
Right, but I guess one difference between sequential and concurrent programs is that at least it's sort of well established that for sequential programs, what you need is pre-post conditions and loop invariants. And some abstract interpretation based tools are going to give you that. And that's helpful. And other analysis tools build on that they know all they need to find is pre-post conditions and loop invariants. But there's no such corresponding notion in concurrent programs. Once we can get a handle on what the proofs look like, maybe we can make more progress there.
Sumit has a point.
To answer your comment, if you can ask other kinds of properties of programs also, right? Besides just saying that whether the program is correct or not. And then if the tool says, yes, then it's interesting. But for example, one problem that I've been working on is like performance analysis.
Yeah.
So you can use the same technology of generating proofs to ask, how long does your program take to run, like symbolic computational complexity or other questions.
So this is good because there is no yes/no answer.
Yeah, this is like quantitative information.
That's right. Because I guess in your analysis, the output of your analysis is not that, oh, your program works pretty good. You don't say that.
Yeah. So more fine-grained classification of functions in your program.
I think
And
it's
another
also
thing that I feel proofs is going to enable is automated program synthesis. That would be useful.
Right. So, but so far, I mean, we are saying that what you have said is that proofs are good as thing, and you know they'll be consumed by other program analyses, right? What, and that is good, but the number of people who write program analyses in this world is very small, right? Most people write, you know, software that does something, and there's an even larger class of people who don't even write software, they just use software. And I don't know, I mean, can we somehow sell proofs to them? That's what I ask. I don't know. Okay.
So I think the economic argument is probably true if you talk about all of programming, but I'm sure there are specific areas where people are ready to pay money to get some sort of certification of correctness. Like if you think of a pacemaker, or if you think of security critical components of your system. So I think the economic argument is, you know, if we actually could do this,
What is
then the people would pay for it.
Are you? Yeah, right.
Yeah, so the application that I was talking about in my talk, I think people would be willing to pay if you have a tool which certifies these apps before downloading. That this app is, there is a proof or a guarantee which you are willing to back it up with some warranty that this app is certifiably not leaking some confidential information. And so instead of downloading the app for $2.99, you say it's $3.99 if it's certified. And I think people would buy it.
But what is to prevent, you know, somebody from frauding, from defrauding users? You know, I can just build some like hokey tool and say, oh yeah, I've certified it.
So that's you know, but that's a social problem. I mean, if the developers or the registration agency understands what proofs are and when certification should be done, and if there is a regulation, that won't happen. So, for example, for the pacemaker, the FDA approves the pacemaker, right? And currently, if you have a pacemaker with software on it, then that software has to be certified. Now, currently, their certification process basically relies on software engineering principles, and basically you have to follow some particular model of software development, and it's not related to proof. But that, one can easily imagine a world where you switch from process to proofs. Like
okay, I see.
And so I think privacy is definitely one area, and the safety critical medical devices.
And also, I mean, security, or like for Sage, I mean, one big next step, I mean, they would love to have a verification tool, something close to it, and using coverage, etc. Because testing, when you stop testing, when you stop fuzzing, and so for the moment, I mean, they have these hundreds of machines running 24/7, all this fuzzing, etc., including Sage, but it costs a fortune, and they never know when to stop. It's a huge problem for them. They would love to have something which even approach verification. But it's true, I agree with your comment, we're still very early.
Right.
But we need, and there's more value in bug finding than in no bug found. But
Actually,
I agree with you, but
actually, I think the
we're getting
situation is even worse than that. For example, I think that as a community, there is no widespread notion, there's no common ground for saying what a proof is. Basically, every tool that people come up with will have its own notion of proof. Yeah, I've proved something. And no two different tools will ever agree, as far as I know, on what a proof is. Because there will be all sorts of random assumptions baked into the tool, because you need those to make the tool work. So I think that to make something like what Rajiv is talking about a reality, there has to be a foundation, so everybody, no matter what technique you use, there has to be some notion of what a proof is.
But it could be a certificate. I declare whatever, you have your black box, your tool, you say, there are no bugs of that type in this stuff. That would be like a weak form of proof. And then whoever wants, you can challenge that, right? That's your certificate.
So how?
Now, are you talking about a proof? Now, I give you, let's say,
no, I mean, I'm talking
a book, basically, of all the tests that were done, etc. That nobody would ever look at. Or like a gigantic formula, etc. That I don't know.
So I don't know. I mean,
but for a certificate,
what is the certifying agency going to look at? Like, what is the
machine checkable proof?
A machine checkable proof.
Yeah.
I see.
But I mean, of course, it's a hard problem. So as I was telling you about that lockless hash table, right? So I don't think we cannot write it. Forget about the tool. I don't think anyone has written a proof of why that very interesting algorithm is correct. And so when there is concurrency, I think writing proofs, we really don't understand how to write proofs of really intricate things, right? I mean, mutual exclusion is I think that's from 60s, and maybe now we understand how to write good proofs of
Okay, let's more questions. Let's thank the speaker.